everyone, thank you so much for joining this video. We're going to be looking at rate equations today. So we're going to define what rate is again, and then we're going to define the terms order of reaction and rate constant, perform calculations using the rate equation, explain the qualitative effect of changes in temperature on the rate constant, and perform calculations using the equation K, that's Arrhenius's equation, and to understand that the equation can be rearranged into the form ln K equals minus activation energy over RT plus ln A, and know how to use this rearranged equation with experimental data to plot a straight line graph with slope minus activation energy over R. We're firstly going to recap the definitions for rate of reaction and activation energy. So the rate of reaction is the change in concentration of a reactant or a product per unit time. So basically it's a measure of how fast the reaction takes place. And the definition of activation energy is the minimum amount of energy required for a successful collision. And this varies for different reactions. So by experiment, the rate of a chemical reaction is related to the concentration of reactants by the rate equation of the form rate equals K times by the concentration of A multiplied by M multiplied by the concentration of B to the power of N. So this rate equation is for a chemical equation of the form x amount of A plus y amount of B goes to form the products. And so what we have is actually that the rate is proportional, directly proportional to the concentration of A to the power of N, where N is equal to 0, 1, or 2. And this power we call the order of reaction. And depending on this order, all the graphs, the relationship between the rate and this concentration will be different. And so because for this XA plus YB forms products, that's why this rate equation is like this, because if we have the rate is directly proportional to A to the power of, let's say, M, and we also have that rate is directly proportional to B, the concentration of B, multiplied by N, then that means we have that the rate is equal to K times this concentration of A to the power of M, and K becomes a rate constant. And we have the same thing for B. So combining these two, we form this rate equation of rate equals K to the power K multiplied by the concentration of A to the power of M multiplied by the concentration of B to the power of N. And M and N the orders of reaction are determined experimentally, so they can't be theoretically given a value. So for the order of reactions, how we word it is that we say the order of reaction with respect to A is M, and the order of reaction with respect to B is N. And K, which is the rate constant, varies with temperature. So we'll actually come to find that K increases when the temperature increases. And the units of K depend on the order of the reaction. The overall order of reaction we would work out by adding up all the orders of reactions. So we have that the overall order of reaction would be equal to M plus N. So the definition of order of reaction is the power to which the concentration of the reactant is raised in the rate equation. So if we have rate equals K times the concentration of A to the power of, let's say, 2, that means that the order of reaction in respect to A is 2. And this is because this is the power to which the concentration of A is raised. And then the rate constant, which is K, is a coefficient of proportionality relating the rate of a chemical reaction at a given temperature to the concentrations of the reactants. Now I'm going to look at the order of reaction, but in a bit more detail. So the first row of this table is the order. So we have zero order, first order, second order. So if we write out the relationship again, so we have rate is directly proportional to the concentration of, let's call it A. So for the first column, we have that n equals 0. So we have rate is directly proportional to a to the power of 0, well, a concentration of a to the power of 0. And for the second column, it would be concentration of a to the power of 1. And then for the third column, it would be the concentration of a to the power of 2. So if we have a look at the first column first, so if the rate is directly proportional to the concentration of a to the power of 0, the concentration of a to the power of 0 is actually equal to 1. And so that means that the rate is directly proportional to 1. But 1 is a constant. And so that means that no matter what you do to the concentration of A, the rate is not affected because the rate is directly proportional to 1, which is a constant, so never ever changes, and it isn't dependent on A. And then looking at the second column, what we have is that the rate is directly proportional to the concentration of a to the power of 1 this time. And so what we get is the rate is directly proportional to the concentration of A. So what that means is that if you increase A by a certain amount, then the rate increases by the same amount. So if we have double of A, then that means that the rate doubles. If you have half of A, the rate halves. If you have 3 times concentration of A, the rate will multiply by 3 times. So it's exactly the same as what you do to the concentration of A. And then for the last column, when you have n equals 2, so you have rate is directly proportional to the concentration of A to the power of 2. So that means that when you double A, so let's say you have double A, so you have A times 2. That means that A squared will be times 4 because the concentration of A doubles. So that means when you have the concentration of A squared, you have 2 squared. So that makes 4. And so the rate increases by times 4. So then you'd have to do rate times by 4. And that's how they've got all of these numbers in the third column. So for example, for the concentration of A times by 10, you'd then do rate times 10 squared. And then when A is halved, so when it's divided by 2, then you do rate divided by the 2 squared. So basically you put whatever number it is of the concentration into kind of the concentration bracket. It's that kind of idea. So that's how you work out how the rate has changed depending on the concentration of the reactant. So how do we find the units of the rate constant? Well, here is the general method. So first you rearrange the rate equation to get K as a subject, and then you write out the units of the rates and the concentrations, and then you cancel stuff out. So it's very similar to what we did for Kp and Kc. So for example, if we had rate equals K times J squared and then the concentration of H squared, what we would do first is we would write out, so what we would do first is we would rearrange to get K as a subject. So we would have K equals rate over the concentration of J squared multiplied by the concentration of H squared, and then write out the units. So rate is measured in, so it's rate is concentration per unit time, which has changed. So therefore the rate units are moles per decimeters cubed per second. And then on the bottom, we have 4 concentrations. Well, a concentration to the power of 4. So we would have moles per decimeters cubed, but that would be to the power of 4. So now you can start cancelling stuff out. I can cancel this moles per decimeters cubed out. I can cancel one of these to make 3. So what we end up with is we have per second on the top, and then we have mole to the power of 3 decimeters to the minus 9. And so our units for this rate constant comes out to be moles to the power of minus 3, decimeters to the power of 9, and seconds to the power of minus 1. Now we're going to talk about the Arrhenius equation. And what this equation calculates is the rate constant, K. So we get an exact value for the rate constant. So there are 2 things to note. The first is that the bigger the rate constant, the faster the reaction. And that's because for reactions, we normally have rate equals K times something. So that means that if this K is a lot bigger, then the rate will be a lot faster. And the second thing is that the higher the temperature, the faster the rate of reaction. And that's because when we increase the temperature, the particles move with more kinetic energy, so there are more collisions per unit time. More of the particles have that activation energy required to successfully collide. So that means that there are more successful collisions per unit time, so the rate of reaction is faster. And now I'm going to quickly go through this equation and what all the letters stand for. So first we have the rate constant, which is K. And this, the units of this depend on the order of reaction. And then this A is the activation energy. And then T is the temperature. And that's measured in Kelvin. The activation energy is measured in joules. And then this R here is the gas constant. And that's measured in joules per mole per Kelvin. And that's usually given as 8.31 because it's a constant. And then A stands for the Arrhenius constant. And this has the same units as K. So it depends on the orders of reaction again. And then this E is a mathematical number, and this is the exponential. And this can be used on the calculator by typing in shift and then ln. So there are a couple of uses for the Arrhenius equation, and one of the uses is to find the activation energy for a reaction. So we start off with the Arrhenius equation, and then we can actually turn it into a different form, which can be more helpful for us. So if we take logs of both sides, we would get ln k, so we're taking natural logs, equals ln of a e to the power of minus ea over rt. And the rule about multiplying 2 logs together is that this is equal to ln a plus the ln of e to the power of minus ea over rt. And then what you can do is we can take this power down. So we would get ln k equals ln a minus ea over rt ln e. A very important thing to know is that ln e is equal to 1. So then what we get is ln K equals ln A minus EA over RT. Now, you don't need to know this derivation, but you just need to remember this equation at the end if you're unsure as to how to work it out. But I like to remember the derivation because even if I do forget this bottom equation, I can work it out. So now using this bottom equation, we can rearrange it to get the activation energy as the subject. And so what we do is we can do EA over RT is equal to ln A minus ln K. And so the activation energy is equal to R multiplied by T multiplied by ln A minus ln K. And that's the formula we have for the activation energy. So then what you can do is plug in all the numbers you have to find the activation energy. Now we're going to look at some graphical analysis. So we have this equation here. If you don't know how I got this equation, then go back to the video where I worked out the activation energy required from Arrhenius' equation. And so we can plot a straight line graph from this equation that we have here. And that's because we know that straight line graphs have the general form y equals mx plus c. And so we can make this into the form y equals mx plus c. So we have y, and we can make ln A equal to c, and then we have mx. And so this gives us that the y would be equivalent to ln K, m would be equivalent to minus EA over R, the x would be equivalent to 1 over t, and c would be equivalent to ln A. And so the graph we get would be like this. So on the y-axis, we would have ln K, and on the x-axis, we would have 1 over t plotted. And then the graph should look something like this, because the gradient, which is the m, this is the gradient, is negative. And so this gradient would be equal to minus EA over R. So the way you find activation energy would be to find the gradient of the graph. So that would be to draw a little triangle here and divide the difference in the y by the difference in the x. You do the gradient multiplied by minus the gas constant. And then this point here, this would be our ln A, because C is the y-intercept. And so that's how you can find the Arrhenius constant. So you would unlog it to find A, and you can find the activation energy by doing gradient times by minus the gas constant. Now we're going to move on to some questions. So for the first question, calculate the rate constant with and without a catalyst in a reaction where the Arrhenius constant A equals 6.92 times 10 to the 6 seconds to minus 1, and the activation energy equals 150 kilojoules per mole without a catalyst and 50 kilojoules per mole with a catalyst, both at 298 Kelvin, using the gas constant 8.31 joules per mole per Kelvin. So the first thing we do is write out the equation that we've memorized. So K equals AE to the power of minus the activation energy over RT. And then we just plug in the numbers. So we have A is 6.92 times 10 to the 6. And then we have the exponential. And then we have the power, so minus the activation energy. And because they've given it to us in kilojoules per mole, we have to convert it to joules per mole, because the gas constant is given in joules per mole per Kelvin. So we need to times that by 1,000. So it'll be 150 times 10 to the 3. And then we divide that by the gas constant, and then times by the temperature, which is 298 Kelvin. So then this comes out to be 3.42 times 10 to the minus 20 seconds to the minus 1. And this is without a catalyst. And then we do the same thing for the one with a catalyst. So we say K is equal to 6.92 times 10 to the 6 exponential to the power of minus 50 times 10 to the power of 3 this time, and then over 8.31 times by 298, and that comes out to be 0.0118 seconds to the minus 1, and that is with a catalyst. And then for B, how many times greater is the rate of reaction with a catalyst compared to without? Well, if we think about it, the rate of reaction is directly proportional to this rate constant. And so if we find out how many times greater the rate constant is with a catalyst compared to without, then that would be equal to how many times greater the rate of reaction is. And so the way we do that is we put the 0.0118 over this 3.40 times 10 to the minus 20. So 0.0118 over 3.42 times 10 to the minus 20, and that gives us 3.45 times 10 to the power of 17. And so the rate constant K is 3.45 times 10 to the power of 17 times greater, and so the rate of reaction is this many times greater as well. So the rate of reaction is 3.45 times 10 to the power of 17 times greater. So as you can see, doing a reaction with a catalyst speeds up the rate of reaction significantly. Before I go on to number 2, feel free to click off the video and try it for yourself first. So this table shows how the rate constant varies with temperature in the reaction of H2 plus I2 goes to form 2HI. Explain how we could determine the activation energy and Arrhenius constant of this equation. So what we do first is we remember that rearranged equation. So initially we had K equals A e to the power of minus the activation energy over RT. But we have a rearranged version, which looks like this. We have ln K equals ln A minus the activation energy over RT. And what we know is the general equation of a straight line graph, which is y equals mx plus c. So if we just match up some of these things to y equals mx plus c, then we should be able to get a straight line graph. And so if we call ln K y, so if we have y as ln K, ln A could be c, and then we would have mx. And so if we make ln K y, and we have c as ln A, and then we have m as minus activation energy over r, and then we have x as 1 over t, then if we plot a graph of ln K over 1 over t, we'll be able to find the activation energy and the Arrhenius constant. And so what we do is we plot a graph of 1 over t on the x-axis and ln K on the y-axis, and then we'll get a graph that looks like this. And then what we do is the gradient of this graph, which is this m here, will be equal to minus EA over R. So to find the activation energy, what we would need to do would be to find the gradient of the line first of all, and then multiply it by minus the gas constant. And then for the Arrhenius constant, we have this c here, and the c represents the y-intercept. So it's this point here where the line crosses the y-axis. And so this gives us our ln A value. So if we unlog this value, then we should be able to get the Arrhenius constant. And the way we do that is, for example, if we had ln A is 6, just as an example, we would put e to the power of 6 in order to get rid of this natural log. So we would do A equals e to the power of 6, and that's how we would find our Arrhenius constant.